Hello, and welcome to Day 4, the OSI and TCP IP model.
Whether you are a seasoned admin or just starting your CCNA journey, understanding how data moves from an application down to the physical wire is the foundation of everything we do. Every piece of data sent over the internet, from a ping to a complex web request, follows a strict mechanical process. Let's discuss about the OSI model, the encapsulation that happens as the packet flows, and the protocols that can be used. Imagine a world where devices from different manufacturers couldn't talk to each other because they spoke different languages. The OSI model solves this by providing a predefined 7-layer framework. It ensures that your laptop, a Cisco router, and a network switch all remain compatible, regardless of who built them. To make this easy to visualize, let's use the post office analogy. Just as Henry follows a 5-step process to mail a letter to Charles, writing it, sealing it, addressing it, and stamping it, digital data must follow a similar set of steps: creation, encapsulation, addressing, and finally, transmission. This movement from the top down is called encapsulation. Think of it like wrapping a gift in multiple boxes. As data moves from layer 7 down to layer 1, each layer adds its own header containing specific instructions for the receiving device. By the time it hits the wire, it has become a frame. Layer 7, the application layer, serves as the direct interface between the network and the end user. To understand this, look at our analogy on the left. Just as a person starts the communication process by sitting down to write a letter, this layer is where the content is first created in the digital world. It is important to note a crucial distinction. While we use software like Chrome or Firefox, the web browser itself is not layer 7. Rather, it is the protocols the browser utilizes that operate at this level. At this stage, the protocol data unit, PDU, which is the specific form data takes as it travels, is simply referred to as data. While we see common examples like HTTP for web browsing, SMTP for email, and DNS here, we will be diving into these protocols in much greater detail in the upcoming slides. Moving from the application where our content is born, we descend to layer 6, the presentation layer, often referred to as the translator. Just as you see in our analogy on the left, where a writer might use a dictionary to ensure their message is understood in another language, this layer ensures that communication is in the appropriate form for the recipient. It acts as the network's specialized translator to handle 3 key functions. Data representation. It formats raw data into recognizable images like JPEG and PNG, or video files like AVI. Encryption and decryption. This is the critical stage where your data is secured for travel and then unlocked once it reaches the destination. Much like layer 7, the PDU at this stage is still simply referred to as data. By the time the presentation layer is finished, your message isn't just created, it's formatted and secured, ready for the session to begin. Moving forward in our descent through the model, we arrive at layer 5, the session layer, also known as the manager. If you look at the analogy on the left, this is the stage where Henry prepares for the communication session by checking the schedule and confirming the post office is open and ready to go. In the digital world, this layer performs a very similar managerial role. It is responsible for establishing, maintaining, and eventually ending the communication conversation between 2 devices. Its primary focus is setting up and monitoring the session to ensure the dialogue remains active as long as needed. You will find protocols like SQL, RPC, and NetBIOS names operating here. Just like the previous 2 layers, the PDU at this stage is still referred to simply as data. With the session established and the post office confirmed ready, our data is now prepared to handle the logistics of the journey. Moving from the management of the session, we descend into the engine room of the communication process, layer 4, the transport layer, known as the flow controller. As you can see in the analogy on the left, imagine a mail sorter at the post office deciding how to send your package. Should it be sent as certified mail, where a receipt is required to ensure it arrived, or as standard post, which is much faster but offers no receipt of delivery?
This is exactly how the technology works at this level. Its primary job is to ensure flow control and overall reliability of the data transfer. This layer handles error checking, data recovery, and regulates the speed at which data is sent, so the receiver isn't overwhelmed. We primarily use two pipes here: TCP, Transmission Control Protocol, which is reliable and connection-oriented, and UDP, User Datagram Protocol, which is built for speed and is used for things like video streaming, where a few lost bits won't ruin the experience. We have a major visual shift here. The PDU is no longer just called data. It has now been encapsulated into a segment. Now that our data is segmented and we've chosen our delivery method, it's time to figure out the path it will take to reach its destination.
Having determined how our data will flow, we now step into Layer 3, the network layer, famously known as the Pathfinder. If you look at our analogy on the left, this stage is exactly like writing the final delivery details on your envelope, specifically the zip code and city. Without this information, the post office wouldn't know which general region to send your letter to. In our digital world, this layer handles the critical logistics of the journey. It is responsible for path determination and logical addressing. This layer performs logical addressing by adding the source and destination IP addresses to your data. It also handles routing, which is the process of finding the absolute best path across the interconnected web of networks to reach the destination. This is where the router lives. It uses protocols like IP, Internet Protocol, IPX, or AppleTalk to navigate the traffic. We have another important visual shift here. Now that we've added IP addresses to our segment, the PDU is officially called a packet. With our packet addressed and the best path identified, we're ready to zoom in from the global network to the local wire. Having determined the path across the global network, we now descend to Layer 2, the data link layer, focused on local delivery. Looking at our analogy on the left, imagine the mail carrier has received your letter and is now preparing to drive it down your specific street to find house 21B. In the digital world, this layer handles the formatting of the message for the local wire through two sublayers. LLC, Logical Link Control. This acts as the final check for error and flow control before the data hits the physical hardware. MAC, Media Access Control. This is where we add the physical MAC address, that unique 48-bit ID burned into your network card. It ensures the message is addressed specifically to the next local device, such as a switch or a bridge. Notice the visual shift in our terminology. By adding these local physical addresses to our packet, the PDU is now officially encapsulated into a frame. Our data is now fully packaged and addressed. All that's left is to turn this frame into raw energy for its journey across the medium. Finally, we reach the foundation of it all. Layer 1. The physical layer, also known as the hardware. In our analogy, think of the delivery truck on the open road. The letter has been written, packaged, and addressed. Now it requires the actual physical highway to move from point A to point B. This layer defines the physical characteristics needed for that journey, such as voltage levels, timing, and cable specifications. Its primary role is to encode and transmit raw data bits over a physical medium. Depending on your network, that transmission media could be electrical signals traveling over copper cabling, light pulses moving through fiber optics, radio waves for wireless communication. At this level, we use devices like hubs and repeaters to keep the signal strong. You'll notice our final visual shift. We are no longer dealing with frames or packets. The PDU is now simply a bit, the raw ones and zeros that make up our digital world. With this, our data has successfully descended from a user's thought all the way to a pulse of energy on the wire. Now that our data has successfully traveled across the physical medium and reached its destination, the process must reverse so the recipient can actually understand the message. This is known as the ascent, or decapsulation. As you can see from our diagram, the direction of flow moves from the bottom up, starting at Layer 1 and climbing toward Layer 7. Think of this like opening the envelope we meticulously packaged earlier. The receiver receives the raw energy, converts it back into bits, and then begins stripping off the headers layer by layer.
A crucial concept to remember for your CCNA is that each header is read and understood only by its corresponding layer at the receiving end. For example, the receiver's network layer reads and strips the IP header added by the sender's network layer, then passes the remaining data up to the transport layer. This continues until all the packaging is gone and the original application data is delivered to the user. Our communication journey is now complete, as the digital letter has finally been opened and read.
With our journey through the encapsulation and decapsulation processes complete, you might be wondering how to keep all 7 layers straight for your exam. To help you out, we use mnemonics, simple phrases that make remembering the order a breeze. Depending on how you like to think about the model, there are 2 classic ways to memorize it. Top-down approach. If you prefer starting from the user's perspective, remember the phrase, "All people seem to need data processing." This starts at the application layer and works its way down to the physical wire. Bottom-up approach. For many engineers, it's more natural to think from the wire up. In that case, use the phrase, "Please do not throw sausage pizza away." This begins at the physical layer and climbs all the way back up to the application. Pick the one that sticks best for you. These phrases are absolute lifesavers when you're troubleshooting under pressure or sitting for your CCNA certification. Here is the pictorial representation of the encapsulation that happens when the PDU travels between the 7 layers. Here is the master summary matrix that give you function, PDU, protocols, and devices used at each layer. Now that we've seen where the transport layer fits into the 7-layer model, let's zoom in on its 2 most critical inhabitants, TCP and UDP. Mastering the difference between these two is essential for understanding how network logic dictates the speed and reliability of our data. TCP is your reliable choice. Think of it as the heavyweight on the scale. It is intentionally slower because it ensures your data is error-free, delivered in sequence, and with no losses. It's the protocol you use when accuracy is non-negotiable. UDP is your fast choice. It's represented here by the feather and the lightning bolt because it is lightweight and built for speed. While it is technically unreliable and offers no oversight or error checking, its best effort delivery is exactly what makes modern streaming and real-time communication possible. It's all about accuracy versus agility. Sometimes you need a receipt, and sometimes you just need to shout. Both are essential tools in a network administrator's toolkit. In many of our daily digital tasks, like web browsing, sending an email, or performing large file uploads, accuracy is absolutely non-negotiable. We cannot afford for even a single corrupted packet to destroy an entire file or garble a critical message. As we saw in the accuracy versus agility scale, TCP is the reliable heavyweight because it provides that essential critical data integrity. It ensures that your work remains accurate by constantly monitoring the transmission. If a corrupted packet is detected, it is immediately identified and resent until the data is perfect. Think of it like the sealed envelope or the digital vault shown here. It's the protocol you choose when the security and completeness of your information are the top priorities. While TCP ensures every single bit is perfect, there are times when speed is the only thing that matters. In real-time applications like VoIP calls and video streaming, speed is the absolute priority. As the slide illustrates, it is actually better to lose a single pixel or a millisecond of audio than to pause the entire stream to fix it. Unlike the rigorous error checking we saw with TCP, here packet loss is ignored. We don't stop to ask for a retransmission because in a live conversation or a fast-paced game, retransmission is useless if the moment has already passed. Now that we've established why speed is the priority for certain applications, let's go back to the reliable side of the house and start our TCP deep dive. Before a single byte of data moves from host A to host B, trust must be established between them. Unlike the fire and forget nature of UDP, TCP uses a connection-oriented approach. This formal introduction process is known as the 3-way handshake. Now, let's break down that handshake into its 3 specific steps, starting with step 1, the request, SYN.
The entire conversation begins with host A, the client, reaching out to host B. To initiate this, host A sends a specialized data packet containing a synchronize (SYN) flag. Think of this as host A knocking on the server's door and saying, "I'd like to start a synchronized conversation with you." As part of this request, host A assigns a random sequence number, labeled here as X. This number is critical because it serves as the starting point for tracking every bit of data that will follow, ensuring that as we move into the actual transfer, nothing gets lost or out of order.
Moving to step 2, the acknowledgement, SYN-ACK, we see the server's response to that initial request. Host B receives the SYN packet and agrees to the connection by sending back its own specialized data packet. This response contains 2 critical pieces of information. First, it includes its own random sequence number Y to track its side of the conversation. Second, it explicitly acknowledges host A's sequence number by requesting X plus 1. This SYN-ACK is the server's way of saying, "I received your request, here is my information, and I am ready for your next packet." As we saw in our 3-way handshake overview, this step ensures that the connection is bidirectional and that both parties are synchronized before any actual data is exchanged. Finally, we reach step 3, the confirmation, ACK, the closing move of our handshake. Host A receives the server's SYN-ACK and sends one final data packet to confirm receipt. In this packet, host A acknowledges host B's sequence by requesting Y plus 1. This serves as the definitive "Roger that" in our digital conversation. As the diagram shows, we have now reached the established state. With the connection officially open, both devices are now synchronized and ready to exchange the actual application data we've been tracking through the layers.
This slide explains the complete 3-way handshake, SYN, SYN-ACK, ACK, that brings the connection into the established state. Once in this state, data flows reliably, with every segment sequenced and accounted for. Finally, just as every conversation has a proper beginning, every TCP session requires a graceful exit to ensure that both devices can free up their resources correctly. This process is known as the 4-way termination. As we see in the diagram, when host A is finished sending its data, it initiates the closure by sending a finish packet and enters a wait state. Host B confirms this by sending back an ACK, signaling that it understands host A is done. Once host B has finished sending any of its own remaining data, it sends its own fin packet to indicate it is also ready to leave. Host A sends one final ACK to confirm, and the connection is officially closed. This structured 4-step process ensures that the termination is mutual and that no data is cut off prematurely, maintaining the reliability we've seen from start to finish. To wrap everything up, let's look at this comparison. At a glance, TCP versus UDP. This matrix serves as your final roadmap for distinguishing between these 2 critical transport layer protocols. Reliability. TCP provides high, guaranteed delivery, whereas UDP offers low, best effort delivery. Speed. As we discussed with the accuracy versus agility scale, TCP is slower due to its overhead, while UDP is significantly faster. Method. TCP is strictly connection-oriented, utilizing the handshakes we just mastered, while UDP remains connection-less. Overhead. You can see the technical cost of reliability here. TCP has a heavy overhead of 20 bytes, while UDP remains light at just 8 bytes. Usage. Finally, remember your use cases. Choose TCP for web, email, and file transfers, where every bit counts, and choose UDP for streaming, VoIP, and gaming, where real-time speed is king. With this comparison in mind, you're ready to tackle any architectural decision or CCNA question regarding transport protocols.